So we just saw in broad strokes how particles influence planets with a focus on the solar system, which is Dave's expertise. But now let's take it from home and move abroad. So exoplanets can potentially be exposed to particle space weather that's orders of magnitude more intense than what happens here in our solar system. So with this lesson, we will find out what happens when we dial it up a bit. Our instructor for this lesson is responsible for a series of seminal papers that opened up the field of exploring the impact of particle space weather on exoplanets. One of those papers actually is the second most cited paper in the journal Astrobiology for the entirety of its existence. And in the midst of publishing that series of field opening papers, she completed a postdoc right here at Caltech in JPL before moving back to her home country, to the Universidad Nacional, Autónoma de México, where she's a senior researcher. And in addition to pushing the boundaries of the knowledge of this field, she has also pushed the boundaries of inclusivity, working to increase the representation of women in the academy. And she's been awarded an honor from her local Congress for that effort. So it is really our privilege to learn about the impact of extreme space weather on exoplanets from somebody who is one of the central pioneers of the field, Dr. Antígona Segura.
Thank you very much, Park. Thank you. Thanks for the invitation. We are going to talk about some drama here. We are going to start with this beautiful show that I bet everybody has seen, an aurora, not in person, but at least a picture. And the fact, and the reason we haven't seen an aurora is because you have to travel very far to see one, to either one of the poles of Earth. But imagine that one day you have one right here in Caltech, and you would think that that is very unlikely. But actually, in 1859, auroras were seen all over the world. Every point that you see there is a place where an aurora was seen in the first days of September in 1859. And even right here, there was a vessel that looked one of them. And you can see all over Central America, there were auroras. And this looks quite nice, but that actually wasn't that nice. What you are seeing here is a magnetometer, the measurement of a magnetometer. It's called magnetogram. It was taken in the Greenwich Observatory. And even if we are not experts on magnetograms, you can see that something is really off there. And with that phenomena, what came is that many of the telegraph infrastructure that was on place in the global north, England, Europe, the US, was born. And basically, the world was without any communication with telegraphs for several days because the cables were just born. And the reason for all this was observed by two persons. One was Hodgson, who was observing the sun's surface, and suddenly he saw this brilliant start of light, this brilliant light. And the other one was Richard Carrington. And so this whole event that happened between the last days of August and the first days of September in 1859 was called the Carrington event. And since then, the Carrington event has been like a benchmark for studies of solar space weather. And what he was doing is to observe some of the solar spots, which were drawn right there by him. And suddenly he saw these bright lights coming out of those points A and B. He related those bright spots with what happened that I described before, auroras all over the world, and all these currents that came and burned the cables of the telegraph. of the telegraphs. And you already saw one of these pictures. Here is what happened on 23, this is the Halloween storm. It was called the Halloween storm in 2003. So what happened here is that you can see all this material coming out of the sun, and all these snowy things that are really particles that were coming out of the sun. And that happened during the Carrington event. It was just like a little bit, this one was a little bit less dramatic than the Carrington event, but anyway, 59% of the space science satellites were damaged by those particles. And what happens is that the magnetic field of Earth is not very useful in those moments. And the reason, this is a model that was done for the Carrington event. So this is what we thought happened during the Carrington event. The coronal mass ejection, so this huge perturbation in the solar magnetic field, push the magnetic field of Earth. So all the particles that were accelerated by this coronal mass ejection were able to get into the atmosphere of Earth, causing all those auroras and all the damages that we know happened in the Carrington event and in some other storms on Earth. And the drama doesn't stop there, because as it was already explained before, these particles affect chemistry too, the atmospheric chemistry. So basically what we have on Earth is that we have this nitrogen, oxygen, and some water in the atmosphere, and the oxygen generates ozone, and we all know that ozone is very important because it covers up from the ultraviolet here. Ultraviolet is not extreme ultraviolet, it's the other ultraviolet, the one that damages the skin and some of the life on Earth. So what happens is that ozone is produced by the photolysis of oxygen. But then when one of these extreme space weather gets into Earth, then water and nitrogen are split, and they produce these compounds that are highly reactive with ozone. And they have these catalytic reactions that destroy ozone. So what happens there is basically you need just a little bit of these molecules to destroy a lot of molecules of ozone, because this is a catalytic reaction, right? So these compounds are not destroyed, but they destroy a lot of ozone molecules. So basically what you get is the destruction of ozone when you have all these particles coming from the sun. So the ozone is destroyed by these highly energetic particles. And how much ozone is destroyed? Well, first, you would think that if the particles come into the poles, basically the ozone would be depleted just in the poles. But for example, for the Carrington event, this is the calculation. This is time, and this is latitude. So the poles are right here, right? So the poles is this. And Caltech is in this latitude. Yes, it's that line. So first, the depletion of ozone lasted by about 2 years. This was like 2% less, 8% less, even almost 14% less ozone than we have usually. So this means that more UV came into the surface of Earth, not only in the poles, but in much lower latitudes. So this is highly dramatic, right? Well, let me introduce you to M-dwarfs. So you already have heard about M-dwarfs. This is a graphic that we astronomers like very much. It's called the Hertzsprung-Russell diagram, although it was created by, all the knowledge you see here was actually the work of women that work in the Harvard Observatory. And, but you know, the guys got the name. So this is the Hertzsprung-Russell diagram, and what you see here is basically the temperature, the effective temperature of the star, and this is the luminosity of the stars, and right here is the sun. And the M dwarfs are all those stars right here. So there are several things. First is that these stars are low mass stars. They have a very, very small masses, and of course they have very low luminosities. They are very, very faint. But the reason we like, well, I like them, but the reason we are interested on M dwarfs is because they are most of the stars in the galaxy. So we are interested on them because we would like to know if they have habitable planets or potentially habitable planets. One of the most famous M dwarfs is Proxima Centauri because it's close, right? It's just 4.2 light years away. So it's, I mean, besides the sun, this is the closest star. And in March 2016, we could see, like naked eye, we could see a flare happening in Proxima Centauri. And what we know is that the optical flux increased by a factor of 68. The total energy emitted by this flare was 10 to the 38.5 ergs. And let's compare this to the sun, right? So what you are seeing here is the total energy flare emitted and how often those flares are emitted by Proxima Centauri. So this is Proxima Centauri. So basically, if you have one of the, I'm sorry, here, okay. So the Carrington event emitted about 10 to the 32 ergs of energy, and those kind of flares on Proxima Centauri are created every 10 years. I'm sorry, every 10 days, right? So for the sun, it's about every 10 years. But for these stars, this happens every 10 days. So this is, to put it in other words, this is like comparing, like the sun is like a soap opera, and these stars are the real Mexican telenovela in terms of drama. And what happens there with the ozone is that the ozone could be totally lost. So imagine you have a planet with 21% of oxygen, and then the ozone would be lost, would be almost totally lost during the first 1 year to 5 years of continuous flaring of the star. So this is huge. Now I'm going to talk to you about another M dwarf, which is even smaller than Proxima Centauri. And this is TRAPPIST-1, and we love TRAPPIST-1 for several things, but let me talk to you about the star first. This is, as I say, very small, very, sorry, the pointer. I shouldn't do this. So the mass of this star is 0.08. The mass of the sun, so as I said, is very, very small, and it's a very cool star. You see, it is like that temperature, 2,500 Kelvin, is cool among the stars. But when we see how much energy this star delivers, then it doesn't look that small. So what you have here in gray is the sun, and in colors you see the energy emitted by TRAPPIST-1. And the trick there is that both energies, if you integrate all those energies, they have exactly the same number. So this is exactly the energy that Earth receives from the sun. And if you go to a place around TRAPPIST-1 where you receive exactly the same total amount of energy, you will get this energy. But as you can see, the extreme UV, the X-rays and the extreme UV, which is here, it's much larger for the planets that are around TRAPPIST-1 than for the sun. And you can see here is like 3 orders of magnitude of difference. And you already heard that this can drive the escape of the atmosphere of a planet, because this is a combination. It's just like the XUV, the X-rays plus extreme UV, hits the atmosphere, and then the atmosphere, it's easier to be blown by the particles emitted by the star. And we are interested in this system because it has 7 planets. I suppose you have heard about it. And this is like a mini solar system. You can, if you have the solar system, the TRAPPIST-1 system would fit in a very small spot right here, even much closer than Mercury. Mercury is at 0.4 astronomical units from the sun. So you will have all this TRAPPIST system right there. You can see here the TRAPPIST system compared to the solar system. And if you have heard about the habitable zone, the habitable zone is this sweet spot where a planet, a rocky planet with an atmosphere of CO2, can retain water in the surface. So the habitable zone is calculated in many ways, but the classic habitable zone would be this green spot right there. And we have 3 planets in the habitable zone of TRAPPIST-1. So we would like to know what happened with those planets. If you have all these X-rays and extreme UV, and certainly you would have a lot of particles and flares from that star, what would happen with the planet? Well, right now we know that, thanks to the JWST, we know that TRAPPIST-1b, it's very hot, and it is likely not a planet with an atmosphere, which, of course, we expected that. For TRAPPIST-C, which is the next one, it seems that there is no CO2 atmosphere. We would expect that CO2 atmospheres are the most common atmospheres in rocky planets, but it seems that CO2 is not there. But that doesn't mean it doesn't have an atmosphere, because actually there is another option. And the other option is this. So imagine that you start with a rocky planet with an ocean and an atmosphere. So this XUV gets into the planet and drives some atmospheric escape, and the water and the planet is being heated, so the water is going to the atmosphere, and the atmosphere is being blown by these extreme particles and XUV radiation. So finally, you are going to get a planet totally dry without any hydrogen, because the hydrogen is going to escape. But some oxygen can be left behind. So you would have these planets, rocky planets, with high oxygen atmospheres. And this oxygen would not be created by life like on Earth, but this oxygen would be created only by the escape of water, as a leftover of the escape of water. Is this a new kind of planets? We haven't seen anyone yet, but maybe the place to test this hypothesis is this TRAPPIST-1 system, because we have a back-to-back system, right? One planet after another that can tell us what happens with a planet, with a rocky planet, as you go farther from the star. So to understand what is going on with planets, is what we do basically is to assume that these stars are creating as much particles as the sun, right? Because we have relationships for the sun. For the sun, we know that if there is this much ultraviolet light, then there is this much particles. So what we have been doing until now, for example, for those also depletion figures, what we thought is we just scale it. Right? If you have this much UV, you have more, then you scale the particles, but maybe that wasn't right. Maybe these M dwarfs are not such a drama queens as we thought before. So actually the space weather on M dwarfs could be less worse than we thought. And the numerical models and the future observations, we expect that we have a better sense of what is really going on with these M dwarfs and if they are really extreme or not in the sense of a space weather. And that's it. I think I was much faster than I thought.